Okay, let's go ahead and get started. Good day, everyone. I'm Jason McDowell. I'm secondment as the Chief System Integrations Officer for ESIG, the Energy Systems Integration Group, and Senior Director for GE Vernova's Consulting Services. Together with Charlie Smith, Mark O'Malley, Karen Wadsack, we serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across 5 action pillars. The foundation of the GPST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium include 1, research and peer learning, 2, technical support, 3, workforce development, 4, technology adoption and support on standardization, and 5, open data and tools. ESIG is the lead on pillar 1, and more information on the GPST can be found at the GPST's website, www.globalpst.org. As the lead on pillar 1, ESIG would like to welcome you to the September monthly webinar of our joint GPST Pillar 1 ESIG webinar series. This series is an addition to the regular ESIG monthly webinar series and focuses on the GPST research agenda and associated topics being addressed by Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and the research community participating in the GPST. In an additional series of webinars and on other 4 pillars of GPST is also being provided in a monthly basis through NREL. For those of you who would like to learn more about the GPST and how to engage, please go to globalpst.org and click on the Get Involved tab. For more information on ESIG, please visit ESIG's website at esig.energy. Next, before we start, I'd like to go over a few logistical matters. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we'll use the Slido platform at slido.com. And to ask a question, please navigate to slido.com and enter the event code ESIG26. That's ESIG 26. The instructions are also at the bottom of the screen you're seeing right now. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote and help prioritize the questions that are submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted to the ESIG website. We also plan to provide a short response to all the unanswered questions after the webinar, so please don't be afraid to go ahead and submit your questions through Slido. So today's topic is on the GPST Grid Forming Technology Implementation Council, providing a status update and outlook on the various initiatives that this council has in store. The GPST system operators and core leadership team have identified 6 enablers to meeting a collective target to operate a gigawatt scale transmission system with 100% inverter-based resources by 2025. These enablers include accelerating and deploying new IBR technology such as grid forming controls, defining new system needs and services, advancements in resource adequacy and integrated planning, enabling new stability tools, models, methods, and metrics, shaping the control room of the future, and unlocking DER integration. From these 6 enablers, 6 implementation councils have been created to drive outcomes in each of these areas, and the first of which is this Grid Forming Technology Implementation Council. Today's webinar will give an overview of this council, share how the council is accelerating grid forming technology deployment through technology demonstrations, model development and validation, codification and standardization of grid forming requirements, and it will also cover existing and future efforts to scale grid forming technology deployment across the globe. It's a great pleasure to introduce our host today. Here to lead us through our discussion is the chair of the Grid Forming Technology Implementation Council, Sten Stoltze. Sten is the Senior Vice President of Engineering at Ørsted, one of the largest offshore wind project developers in the world, responsible for a $20 billion pipeline of large infrastructure projects in the offshore wind and transmission assets area. Sten has served this leadership role for the past 8 years, before which Sten worked for over 20 years for the Danish multinational FL Schmidt that constructs cement and mining projects on a global scale, where he ended his long tenure as head of engineering in the cement division. I greatly value Sten's leadership and contributions to the GPST and the industry, and I'm looking forward to hearing what he has to share with us today. Okay, just a short reminder once again to use slido.com, event code ESIG26 to ask your questions. And let's go ahead and get started. Sten, it's a pleasure to turn over to you now. Please take it away.
Thanks a lot, Jason. Appreciate it. And thanks for your good and nice welcome. And welcome all, also from my side. Good to see that so many people are here. We're going to spend some time on the topic, but also leave a little time at the end for Q&A. Now, as Jason mentioned, I'm sitting in say the hot chair in the middle of everything. At least we tend to think so as a developer. We develop offshore wind farms in US, in Europe, and in APAC. So we are as global as the industry gets for now. So far so good. Let's dive into the presentation. Now the GPST, as Jason mentioned, has 5 key areas. I'd just like to spend a little more time on these. First of all, we have the first one to the left of this slide, system operator research and peer learning around cutting-edge research to create new system solutions and globally disseminate and infuse new insights through peer learning. This is an track that is very key to the entire GPST setup, but also supports across to the other four work streams. Number 2 around system operator technical assistance, which is more around the implementation to support and scale the solutions we find. We have the third one, which is around foundational workforce development, which is very much around building the workforce for the future, making sure that the workforce we see also in developing countries, gets the knowledge that they need to further develop what they do. Then it's around the localized technology adoption support. And then finally around open data and tools. And the last 2 ones is very much around first of all, the teaching and the training in that space, but also around finding the tools, using the tools, building new tools that we can use across the 5 areas. Now on this next slide, we will have a look at the enablers and implementation. And I think one of the critical points on this slide is really the part in the light blue on top of it. The goal is to enable an operation of 100% IBR transmission system by 25, or other regional goals, meaning that we want to be able to operate a system in island mode at 100% inverter-based resources without any supporting mechanisms other than the grid in itself and the wind farms and the solar systems and the batteries that feed into the systems. We have a number of enablers that will help us achieve that. To the left of the slide, we would have a clear definition and adaptation of new systems. We would have advanced techniques to define and ensure resource, energy, and flexibility adequacy. We would have deployment of advanced technology capabilities, such as grid forming, to meet grid needs and provide services. This is the thing that we will also spend a little more time on. We would have refined stability tools, models, methods, and metrics, as well as advanced operation capabilities, and again, DER, architecture, operation, and impact. Now, these enablers are there and to be implemented through some top projects, and the top projects we do have enlisted to the right of the slide. In particular, the number 3 is of interest here, the grid forming inverters, grid forming implementation council. This is where we kind of pave the way to the future around how is it the system of the future will look. It will look at the standards we do have. It will look at developing also new standards. It will also look at how does this field really work now, and how will it look in the future. Now, to take a little step out of that, the grid forming implementation council is built upon some basics. First of all, it's around breaking the chicken and egg cycle. As a developer, I know that one thing is that what we need to get out and do, we need to find out what is it we need to put onto the grid, and the grid operators are also looking at that. The regulators are looking at it, and the OEMs are trying to feed components into that. On top of that, we would have software developers and others that are also looking at this space, trying to develop the new tools. Now, the chicken and egg, say, concept came out through the initial discussions and the thinking we had around that. And it is around identifying the grid forming features and requirements that system operators would need. It's also around supporting technology demonstration and deploying grid forming resources. Then it's around the grid forming resource procurement, what we as developers need to do, looking ahead, making sure that the things that we do want to implement, that it is in fact available at the time we want to do it. And then it's all around, building some standardization, some codes, some interconnection requirements, some way of working that we can use across the globe. It may be different from one location to another. It may be different from one region to another, but we will have to find different ways of building a fully IBR inverter-based resource grid. Now, the way we want to work with this is we want to get the people in the room and start some discussion, and we want to have some discussion with the system operators, obviously, project developers, OEMs, and software developers, and so on and so forth, so that we can have a common understanding of where we are. Now we are building, say, the tracks as we write them, so to speak. We have some people in the room already. We have from the developer side, if we start with us, we have Ørsted, we have Enel, we have Inverter, sorry, Energy, we have Zenobia, and we have Nextera. And we would also expect to have a few others on that list going forward. We have on the system operator side, we have National Grid, we have AMO, ERCOT, Energinet, and so on and so forth. We would have some of the operators that are furthest developed in this space that can do the most already, and still they struggle. Still, these operators, they struggle with, how do we take this to the next level? So we have those in the rooms. We would have the OEMs, obviously. We have GE, we have Smart Wires, we have Siemens, Siemens Gamesa, Renewable Energy, and Hitachi. And we would expect to have more also in that area. So we have in the room some of the key players in this space, and we would have the opportunity to really build something together. Now, one of the things that we of course discuss once in a while is the fact that we all bring IP into the room, and we want to make sure that people are safe in that space, so that you don't need to bring anything that is your personal IP that you don't want to share. On the other side, on the other hand, we have a number of things we want to achieve together. So I think we have an opportunity here to really share and get some traction on that. Now, let me just change to the next slide. the tasks and timeline of what we intend to do. And this is really, a lot of work in progress, but also things that we want to do. Of course, define grid forming services. We'll get back to that. We want to define some technology demonstrations and develop also a demonstration plan. We want to document performance requirements ready to be codified, as well as create a roadmap of requirements ready to be codified and outline studies and research needed aspect that cannot. And so we want to make sure we want to, build the future in theory as well as test it. And the important thing of this is to get things tested. So we want to identify the funding, research, and the studies that we need, and also support development and provide guidance to OEM. So we want to make sure that we build some of the tests that we need to build, the tests that will drive this forward. Now, we had a discussion in the team a few days ago, or yesterday, in fact, I think it was, around, this will happen anyway, won't it? Yes, it will, but it will take 10 or 15 or 20 years, and we cannot really wait for that. So we want to push ahead with some of these things. When we get to 25 and beyond, we also want to make sure that we get a full set of requirements, or a full set of equipment to be tested and deployed around the world, as well as grid forming operating experience acquired by leading system operators, and get that shared also globally. And I think the one of the points here is that some of the TSOs, or the founding system operator, the FSOs, are the ones that are most advanced in the world. So they have a lot of knowledge already they can share. But it's also obvious that they are in a situation where they also need to build more knowledge. They would have, the one that is most advanced would have a renewable penetration or an IBR of around 70%, and the rest will be lower than that. So we are, fairly progressed, but it's also, it's getting to a point where it gets more and more tricky as we want to take out the last part. So it is quite obvious that this is something we need to push on. Now, excuse me, yeah. So we want to go into selecting the initial grid forming demonstration pilots, and I think the immediate objective is, of course, to demonstrate the grid forming performance, the capabilities and the models, and the things that go around the initial grid forming demonstrations. And I think on top of that, we would have the ultimate objective, which is of course a series of field tests and model validation that would put it all together in a large gigawatt scale system. Now, some of the demonstrations that we're looking at is out there. They're not quite operational yet. I think we have a number of battery storage systems at AMO. We would have also a handful of grid forming battery systems at National Grid. They're not quite there where they are as such grid forming, but they're getting there. We would have also ERCOT with a grid forming demonstration in Texas. And there will be a few other demonstrations that are out there already. Now, most of these are based on battery storage. And I think it's also fair to say that we want to make sure that also other types of equipment are being tested, that we would have a fuller picture of what will happen. We'll get back to that on the next slide. But what it also wants to do is we want to make sure that we use the existing projects as first phase, so to speak. Also, we want to take a look at what would be the next level of tests to be done. We want to take a discussion with developers and OEMs to identify those, and then we want to make sure that we work with also system operators and developers to find new demonstrations across the grid, basically. So that is what we want to do. The way it falls into a larger plan perhaps could look like this. And this is an attempt where Jason and I scribbled on a whiteboard. This is an attempt to make a roadmap of the things we intend to do, of the ongoing things and the white spots. And if you take a look at the left of this slide, we would have all the performance parameters, the frequency control, voltage control, harmonics, and all that, so on and so forth. And then we would have the left side of the blue part is what is the operator of the grid is kind of controlling, and then we would have what is the generator of the power controlling, and then we would map out the things that are ongoing, and we would also have an opportunity to find or identify the white spots. And I think the white spots are quite important in this because, you know, there's a lot of things ongoing, but and that's all fine. But I think if we want to make sure that we've also identified the white spots so that we can get things done there as well. Then the direction of travel is, of course, from left to the right as such. And you end up to the right with 100% IBR islanded mode grid, meaning that, you know, you would have, and there's not one way through this, say, maze or this roadmap. There will be different ways that would get you there. You could have a certain element of frequency control, a certain element of voltage control, and so on and so forth, that would get you to 100% island mode. You could also have a different way to that. If one way kind of is out of operation, there will be a different way to that, so that we get the full picture of what does it take to be a 100% IBR island mode grid. Am I missing something, Jason? Or should I just move on?
No, Sten, I think you covered it well. And I think, you know, the advantage of talking through the road mapping exercise and looking at the grid needs and the services that need to provide perhaps different elements of grid support with higher penetrations of inverters, you know, are very much a part of this road mapping exercise, that we want to show what are the areas that the equipment needs more work in terms of capabilities for the equipment to work together better. And then how does all the generation and the load balance with higher penetrations of inverter-based resources? What does that low generation balance look like? So having the capabilities to look at all of these different elements and how they may individually need to progress, but ultimately how do they need to progress all together, is really part of what this road mapping exercise really is. So I think you covered it well, Sten. Thanks.
Yeah. And I think that leads me to another thing, and that is the element of control. How is it we control this entire system? Who dictates the frequency of the voltage, and who dictates and who follows, and who when one trips out, who does then take over, and all this and that is becoming, you know, more and more critical as first of all the inverter based amount of energy it goes up, but also as the grid expands as a whole. Then we would have this one, which is, of course, you know, we started to populate this, and this becomes very, very, detailed. And I'm not sure I really want to go into too much details here. I think it is our attempt to plot in the things that are happening just now. It is our attempt to generate the overview. It is a work in progress. It does not work with the white spots yet. So it is a snapshot in time, what we have, but it is also something that we need to build on further. Then if we take a little step out, we would have here the And we've used a couple of slides from Julia that some of you may have seen at the last seminar. But we just want to, we think this is pretty good, and we want to use this as a couple of examples, or at least some examples. And we have here to the left of the slide, we would have a grid that is 0% IBR. It's very strong. There's nothing to well, I don't know if there's nothing to make this, to push it out of control as such, but it's very stable. And you would have, for the initial part, you would have 10 or 20% IBR. You would have just grid-friendly features as such. When you move up into the space, you start to have a little more need for grid supporting features. And when you get up into the space of 50 to 75, you need to have some sort of grid forming features, or at least you must have additional equipment, keep that running, even though it is not needed, so that you could have the grid stability. Now, the point here is that we are at that point now, but we can go the last 25%, so to speak. We can get to 100%. We need to identify what is needed for the system. We need to identify what grid forming capabilities we need and to what extent. We need to be able to of course, produce and deploy those. But it is possible to go to 100% IBR and having a strong grid. But it will take an effort also from this team. And it's, I mean, as it's stated in the bottom, if you can deploy grid forming capabilities, it is cheaper and it is faster than adding new transmission assets. So I think we're tracking in the right direction. Now, looking at this one, this is a history lesson. It does not go that far back. It goes only to around 2000, but this is where the grid code started for the inverter-based resources. This is where you can see how in 2007 we had the first efforts around harmonization. We would have the Scandinavian and the German system operators working on that. Texas following in 8, moving up towards 15 and 16 with US NERC and the NCOE, and then the US NERC guideline in 18, and the up to the point where we had this major harmonization effort in the EU that well, that was 20 years, in the making, coming out in 2019. So this is all around harmonizing the effort and pushing it forward. Now, the grid codes as such, how can I put that? Yeah, no, maybe not. I'll pass that one. But I think the key point here is that it took us 20 years to get where we are. We cannot take another 20 to get where we want to be honest. We still don't have a fully harmonized grid code in US. We do have some harmonized grid code in Europe, but we still need to get even further out there. And it's not that we have not had a lot of effort. I think we have been working on over the last 3 years. You can just look at this list of technologies. This is ESIG and GPST coming out with all the way from the beginning, the NREL report on grid forming inverters, the NCOE, the NERC on grid forming again, and then so on and so forth. So there's been a long list of activities over the last 3-4 years, all feeding into the same topic around grid forming and grid stability. The initiatives and standardization area, which is a little more, could be a little more long-haired. We have other things going on as well. We have the SIGRE ongoing with the development of grid forming converters. We have IEC coming up with a proposal on joint working group. We have Senelec and we have IEEE with their work around this, all the way and up until the Hawaii grid forming specification as well. So there is a lot of things ongoing out there in the world that we need to take into our work. Then we have the demonstration proposal, and now we dive into a little of the things that we want to spend some time on and some money on, to say. And this is also very busy slides. If we take it from the left, really, we have some different grid forming inverter specifications. We have the national grid requirements, we have the NERC recommendation, and we have osmosis and VDE requirements, and we have the Hawaii experience, and then that feeds into, together with AMO and Energinet, we feed that into our grid demonstrations, and the field where we want to test performance under normal grid operations and also under outside normal grid operations. We want to test it with additional behavior. We want to test how it works in modeling and documentation. Under normal grid operations, there's a lot of things that has to happen. We need to autonomously support the grid. We need to provide positive damping. We need to have coordination controls. We need to have robust operation, and we need to have voltage balancing and other things happening under that. And then we would have an outside normal grid operation. This is where we would have, how can I put it? I think we had a rough experience ourselves in August 19, when we ended up taking out the subway of London with our Hornsea 1 wind farm, where we did not have a fault right through behavior. And ultimately it was an error on a transformer station somewhere onshore, and it was blowing very much. Cladding fell off into the electrical equipment. It sent a shock wave through the system. It took out a biomass fired power plant, and that took out then our offshore wind farm. And then by the end of the day, or not the end of the day, shortly after, the metro in London stopped. So it was kind of and I think we did not want to happen. And there was certainly something around right through behavior on that one. There was also around the frequency response was also not as it was supposed to be. But there's also other things that we put into that space. What happens outside normal grid operations, phase jumps, voltage steps, and so on and so forth. On top of that, we could have on the top right the additional behavior, black start, voltage, harmonics, secondary voltage, and so on and so forth, as well as we need some model and documentation on this as well. This all feeds into a demonstration plan. We want to develop project plans. We want to we put out here we put 5 million per project plus 5 million project management support. I think it's rough figures. I think we want in this track alone a total of 90 million, if I'm not wrong. So there is some work to be done. That's obvious in this track. Now, if I go to the next slide, we want to build the framework, and now we are around the performance requirements again to be codified, and those that require further definition. And that's also around building the grid forming requirements, leveraging the existing grid forming, and also taking the test plans that we do have, but also find what are the new test plans we need to take in. And then, of course, coordinate with Pillar 4 on standard development. We want to create a roadmap that is ready to be codified, and also research aspects that can't be codified. We want to identify the funding for this, and then we want to identify and support development of grid forming designs by manufacturers that can meet codified requirements. So, in essence, accelerate really what needs to be done in this space. Not as such. Let's basically do what we need to do, just do it faster. That's what we want to do. Then I think we have the second last slide, or perhaps the last slide, is really accelerate and actions around our next steps. And that is really, we want to take testing plans. We want to make the testing, getting that up and running. We want to do the single pilot testings, as well as we want to do the multi-grid forming testings. We want to develop grid forming demonstration plans, and it's around simulation and testing. It's around requirement setting. It's around grid forming model metrics and research and innovation funding also. And then we want to engage the regulators in grid forming discussions for developing a framework of baseline grid forming requirements. So it's very much around testing also in more than, multiple grid forming, working together and taking the learnings out of that and engage into the discussions with regulators. And some of the high priority next steps is, of course, to complete the roadmap. It's accelerate the grid forming development and deployment. It is create a common framework for grid forming. And then it's define the expectations for the future that are realistic, implementable, and at a workable pace for society. Now, what does that mean? That means that we are quite busy. It also means that we need to do a heck of a lot more. It means that we need to accelerate what we do, and it means also that we need more money and we need more time at our hands. But this is where we are. And this is where I say thank you. And I think we open the floor for questions, or maybe an initial comment from you, Jason.
Thank you so much, Sten, for walking us through that. Really exciting to see a lot of the input that we're getting on this platform from not only the system operators that are embarking on a new phase, right? Especially those system operators that are experiencing high levels of inverter-based resource penetration today, but having the collaboration between the system operators, the developers that are installing the equipment and having to operate the equipment and live with a lot more uncertainty when it comes to riding through system disturbances and having equipment technology work in a grid that is far more diverse today than maybe it has been in the past. And obviously bringing in the OEMs as well on this platform to talk about things in ways that we need to talk about them to accelerate the dialogue about how to identify system risks, how to understand where those risks translate into new technology capabilities, and then mitigate those risks with a host of different aspects, a host of different controls capabilities, a host of different technology capabilities, and operational capabilities, right? So that's why it's exciting to see that there's this collaboration happening across GPST. And I see that there's a lot of questions that are coming in. So thank you, everyone, for going to slido.com. Again, the event code is ESIG26 if you'd like to log more questions. And let's go into some of the questions now, because I think a lot of what we'd like to pull on in terms of the next aspects of the council is embedded in the questions. So for the next 20 minutes or so, let's go over to the questions. The first one, and Sten and I will be going through these questions together. Sten, I'll give you an opportunity to chime in on each one, and then if you'd like to punt it back to me, however you'd like, let's tag team. The first question is, what are the advantages of grid forming controls over grid following controls in a grid that still has a significant amount of synchronous resources online? Or is grid forming only relevant for 100% inverter-based resource grids? You have a thought on that, Sten, or would you like me to take that?
Yeah, well, I have a thought. It's not really needed in the very early phase, is it? Because you have a very low penetration of renewable or inverter-based. But pretty soon you will need it. We see it in the countries that are further developed right now, like say say UK as an example. We see how their massive build out of renewable has quite an impact on the grid now, and I think it's I don't know, is it safe to say that they are maybe not struggling, but at least, you know, they have to walk a very narrow path to make sure that they have enough grid forming and enough of the grid stabilizing equipment. So I think it's not super needed for the ones that are very, very early stage, but it will very soon, and also sooner that we've seen now in the countries that have come far. It will sooner than what we've seen there. It will become relevant in other parts of new countries that take it up like that. Jason?
Yeah, sure. I think that's well put, Sten. And I think you know, there's different elements and different aspects that we have to consider and remember about grid forming, and that grid forming isn't just one thing. Grid forming can take on different forms to provide performance and capabilities for a multitude of challenges in the grid, one of which is to solve a lot of the more complex control interactions and stability related issues between multiple inverter-based resources in very weak grids, right? So that's one aspect of having grid forming controls act like a voltage regulated voltage source converter that acts more like a synchronous machine to stabilize the grid and avoid control interactions when there's high penetration pockets of inverter-based resources. So in those cases, you don't necessarily need to have a 100% IBR complete grid in order to show and have the benefit of the grid forming controls. But where you do need, where it does have the benefit, is if you have very high penetration pockets of inverter-based resources, close to 100% locally, or high penetration locally, that's isolated or disconnected from the rest of the system, maybe that has synchronous machines farther away. Grid forming can still play a role in that area where there's a higher percentage, maybe close to 100% of local penetration of inverter-based resources that may still have stability challenges in those pockets, right? And the other aspect is supporting frequency and frequency response overall. There's many questions that talk about, you know, what does frequency response look like? What does secondary regulation look like in close to 100% penetration grids? What we're talking about here specifically in grid forming is what is the performance typically due to large system disturbances in a very short amount of time during and after that disturbance? And how do the controls respond? How are they stable? How do they support voltage and frequency control? And maybe how do they support more advanced capabilities like system restoration and black start if you have pockets that are islanded and happen to go black? How do you recover and operate in environments with no other synchronous machines online? So those are all different aspects of grid forming controls that have benefits to the grid at higher penetrations, of course, but particularly when the local high penetration of many inverter-based resources and weak grids grows, as well as having a more benefit in a more global sense, where we have an entire grid, let's say an entire islanded grid that is operating at or close to 100% for support of, you know, rock-off arresting power, inertia, and frequency response very quickly after a disturbance happens, right? So grid forming is not one thing. It's also not a silver bullet to say grid forming is going to solve everything that's needed in 100% grid either. There's a lot of questions that I saw, rightfully so, about, well, what are the other aspects that need to be considered? And grid forming is a great tool in the toolbox that can solve a lot of issues that are challenging to existing grid following resources alone, but it doesn't mean that grid following resources need to be retired and changed over automatically. It's a matter of optimization of making the most out of the capabilities out of grid following resources and augmenting the capabilities with grid forming controls so that you can achieve higher penetrations across larger systems. The second question that came up, which is related, and it's about this penetration, this operating 100% IBR across the systems that we talked about. And the question comes from Andrew. He says, does the 100% IBR target exclude all synchronous machines, including synchronous condensers? And so the target itself, this operating 100% IBR transmission system by 2025, it's an aspirational target to be ready for the instance when we only have inverter-based resources online, and when the fuel allows, when the wind and the sun allows, and the amount of penetration of wind and solar and batteries and other inverter-based resources for that matter may be online supporting grid stability like FACS, and also, of course, there's HVDC in the mix in certain grids as well that are inverter-based that can contribute to challenges. So the 100% target is a bookend to say the system operators want to be prepared when it comes to having 100% of the energy served. Maybe it's for an hour or 2 or 3 or 5. The system resiliency, the system reliability needs to be maintained in those hours of that 100% capability, just like it does for all other 8,000 plus hours during the year, right? 8,700 whatever hours during the year, that there wouldn't be 100% penetration. The reliability still needs to be maintained. So it's that readiness to say we want to have a grid that's capable of operating reliably, riding through disturbances, and successfully integrating and being interoperable between all of those resources. And that's what we really mean by having a 100% IBR target is an aspirational target in the regard of being ready for it when it comes. Sten, anything else to add there before we move on?
Well, nothing else than, being ready when it comes. I think it's already here, isn't it? I mean, we already have those hours and days of 100% IBR in these more advanced system operators grids. They still keep some of the old equipment, so to speak, running to stabilize the grid, but we do see now the situation with 100% renewable for shorter periods of time.
Excellent. Yeah, thanks, Sten. Really great point. Let's move on to the next question. This comes from Schengen. And the question is, could grid following inverters be converted to grid forming inverters using add-on hardware modules? And if not, how could we harmonize grid following with later grid forming inverters in the grid? That's a really great question. Sten, would you like to take this, or do you want me to cover it?
I think maybe you should start then, because it becomes a little technical.
Yeah, no problem. So it really, grid following capabilities and retrofits, it will be based on the type of generation technology. There's different aspects and different, I would say, call it flavors of capability, whether you're just changing the software or the controls, or whether you really need to update the hardware on different types of resources. On resources like batteries, when you have the ability to change the control from a current regulated or a current injection source to a voltage regulated voltage source converter, and you're not changing any of the overall hardware that's associated with that, just changing the control mode, that is much easier. And those retrofits can be done. On different resources, like on wind plants with drivetrains, for example, there is an implication on the overall stress that grid forming controls may have and will have on the drivetrain of the wind turbine. And in terms of what capabilities are there to have grid forming on wind turbines at all, and then the second question about if you can retrofit those, it's really dependent on the overall base design and how the stress can be managed on the drivetrain to accept grid forming capability. There's more advanced grid forming capability that can further push the envelope in terms of frequency support, in terms of having wider ability to ride through angular events, angular disturbances, voltage disturbances, ride through events, incorporating black start. Those more advanced capabilities tend to need to have an energy buffer or energy storage associated with the grid forming. And it needs to be accommodated also in the overall design of the life cycle of the wind turbine. So wind is a little bit I would say more advanced and difficult to design for grid forming, just because of that drivetrain stress implication. But starting with batteries, the grid forming capability to have grid forming controls in batteries is certainly there today. We've got a lot of examples of batteries on the ground today that have that capability. More batteries, as you saw through the presentation, are going to be installed in the short term. And having more grid forming capability there is the low-hanging fruit. So there's a start, but there's also development being done across the board to have grid forming, other grid forming resources like wind, other grid forming resources on the transmission side, like fax devices. We have certainly a voltage source converter type HVDC that's grid forming that can be coordinated with other resources. So there are many different elements that we're going to be including in the council to look at demonstrations. And as Sten said, we're really looking to not only demonstrate one of these resources in their grid forming capabilities alone. That's certainly one of the important steps. But more importantly is how to demonstrate a grid forming set of batteries with eventually maybe some grid forming wind in a grid with grid forming transmission devices, in a grid with HVDC, and making sure that all of that works together so that there are no surprises and that there is true interoperability between grid forming devices to other grid forming devices to grid following devices. And that's one of the next questions that I see about how do you optimize the coordination between grid forming and grid following, but also grid forming devices with other IBRs and synchronous machines, right? When the synchronous machines are online. So that's the overall objective that we're trying to achieve. Let's see. This is a good question. This next question is around what do we need to consider, not only about the resource side, but what about the load? This target of 100% IBR is really meant for looking at what happens when we have 100% IBR sources on the system, IBR generation, IBR, IBR based and grid forming based StatComs, HVDC, that sort of thing. But the question about the load is a very critical one. And it's one about, well, what is the load going to look like going forward? And how do we need to accommodate that? So this is something that eventually is a broader question going beyond just this grid forming council, but it generally is a very important question on how we look at development of new tools, models, methods, metrics, as we talked about. How do we take into account integrated planning when the load is changing, when the load is becoming more power electronics based, when the load has more energy storage, let's say with electric vehicle proliferation as well, right? So with so many things changing, there's many different aspects that require new ways of analyzing, new tools, new models, more fidelity, and then being able to real time understand what the implications are. So this investment in control room of the future is a very big aspect. The visibility of control down to the load and understanding how the load impacts is a very big part of GPST, well beyond just this grid forming implementation council alone, but something that is very much a part of the overall fabric of what GPST is looking to resolve. Anything to add there, Sten?
Well, yeah, well, there was a lot of talk around the load there. I think I don't know what to add, to be honest. I think that You said it all there, Jason.
Great. Let's move on to a couple other questions. We have about 5 minutes left. Eric asked the question, can we talk about the case of secondary frequency regulation using inverter-based resources, and maybe how it's performed, maybe through virtual power plants and the like? Yeah, that's a good question. It goes beyond the need for grid forming. Grid forming, as I said, is very much aligned with what happens in the first milliseconds in a very fast time frame after a disturbance happens, and then everything in the longer term on primary frequency response, on secondary response, on regulation, on balancing. It really doesn't matter if you have grid forming or grid following resources and or synchronous technology for that matter. That's a different question about having the capability of supporting the frequency out of either grid forming or grid following inverter-based resources in combination with the governor response of synchronous machines. Obviously, the synchronous inertia and the capability of grid forming controls, if they have the ability to, support the actual rock-off response and mitigate a frequency decline during a system event. Those things are really going to matter in terms of the overall frequency response. For the secondary frequency regulation, that's more a matter of system operations and how integrated planning works together to coordinate the capability of an inverter-based resource to move up and down based on a command coming from the system operator or automatic generation control, making sure there's headroom and capability to move around. And in today's systems, still most of that secondary regulation and a good part of that primary regulation actually is still taken on by synchronous machine technology that's dispatchable. But there are more cases around the world now that are using inverter-based resources to actually provide the secondary regulation. The wind plants, solar plants being on AGC. They certainly have capability to do it. It's a matter of operations and keeping enough headroom and footroom in place to be able to move around and do that. So it's not a grid forming topic really, but it's something that's really important as we get to higher penetrations of inverter-based resources to make sure we have enough regulation capability to balance the load. Thanks, Eric. I see, Steve, you have a lot of questions here and a lot of comments. Thank you for participating. And I think this is one of the comments that you put in place. Your comment is about the different modes, normal mode and withstand mode, being identified as separate operating requirements in Great Britain, and other clarifications to the grid code and security standards. I think that comment is well placed because I think in Great Britain, a great effort recently was to design and implement grid forming capability into the grid code. And withstand capability of angle shifts, of phase jumps is one aspect of that, but having a fully defined set of requirements for grid forming controls in National Grid's grid code, I think has been a really great push forward in the industry to say we now have a set of requirements that defines grid forming capability. As many of you know from some of the previous webinars, National Grid implements that grid code with non-mandatory requirements, but that grid code ultimately qualifies a grid forming device to be able to provide a minimum level of support for control stability, for rock-off response, for active power, for damping, and many other aspects that are really important to Great Britain's electricity system. And it's implemented actually through a series of market products for dynamic voltage support, for inertia response, for system strength and short circuit. That is really a very neat way that you can deploy the amount of grid forming that you need in different system operating conditions, and still maintain the system integrity and reliability as is needed. And I think it's a really great way that GPST has been able to take that lesson learned from Great Britain and National Grid and really share that among other system operators that are starting to do the same thing, coming up with other grid forming capabilities in their grid codes that can be implemented not only as requirements, but non-mandatory requirements that qualify a grid forming resource and be deployed in different mechanisms like markets where there are markets, right? So great comment. Thank you for that. Maybe one more question and then we'll wrap it up. Tony has a comment, said that there needs to be some amount of stored energy in excess of the current grid balance in real time. And is there a total target in the amount of megawatt hours available for that energy or need? I'm not sure, Tony, if you're really talking about stored energy in terms of the grid forming capability or stored energy just to balance the system out if we have a lot of inverter-based resources in the longer term. I think that is a question that is well beyond just the Grid Forming Technology Council capability, but that's something that goes into more of the integrated planning to say, when you have 100% inverter-based resources, where does the balancing come from? Does it come from batteries? Does it come from operations? Do you overbuild, right? Do you look at optimizing the amount of wind and solar and batteries to balance out the load at any particular time? All those are really relevant questions that we're going to be tackling in some of the other councils. The Control Room of the Future is going to be a very big part of that as well, to understand situational awareness and how to visualize when you have high penetrations of renewables, where the balancing comes from. So all of those things are going to be a very big part of what we are doing in the in the GPST going forward through the councils. But it's not only a topic that we're covering in the GFMIC. So we have a lot of other questions. Thank you for all the questions, and we'll be able to get to those by responding to you after everything is done. But since we're at the top of the hour, would really like to wrap it up and thank Sten for this really informative webinar on grid forming technology. As I mentioned earlier, we're going to have a link to the video after this session is wrapped up, and the video will be posted so you can have the slides and the video available. And we'll get you some answers to the questions that we weren't able to get to as soon as we can. Again, really appreciate your participation. And if you'd like to stay engaged with GPST, I'd like to invite you to participate in the next webinar on October 2nd. This is an ESIG webinar on the need for intertie optimization by Hannes Pfeifenberger and Norman Bay. I'd also like to invite you to attend the ESIG Fall Technical Workshop in San Diego in the last week of October, where we've got another great lineup of panels and working group discussions. Further information about all the webinars can be found on ESIG's website at esig.energy under the Events tab. And if you're invited also to learn more about GPST and these webinar series through GPST, found at globalpst.org. Sten, want to thank you again for this timely webinar, and thank you all for your interest. We look forward to seeing you again in the future. And in the meantime, everyone, please take care, please stay safe, and thanks again for your participation. Have a great day, everyone.